All right, welcome to The Explainer. Today, we're going to pull back the curtain on one of the unsung heroes of, well, basically every office or even home network. We're talking about how we went from total shouting matches to really smart, directed conversations. And it's all thanks to a pretty incredible evolution in this little box you've probably seen a million times but never really thought about.
See, think about it for a second. How is it possible that hundreds of computers all in the same office can talk to each other at once without it just becoming complete and utter chaos? I mean, all these devices are on one network, what we call a local area network or a LAN, and they're all trying to send and receive data at the same time. The whole answer really lies in this amazing journey from a really simple and frankly loud device to something a whole lot smarter.
And that journey, it's all about moving from what we used to call a hub to what we now call a switch. The best way to think about it is this. A hub is like a shouter in a super crowded room. It just hears one thing and then screams it out for everyone to hear, whether they needed to or not. A switch, on the other hand, is way more like a smart postal operator. It looks at a message, sees the address, and then quietly and efficiently delivers it only to the person it's meant for. Big difference, right?
Okay, so let's really dig into this. To get why switches are so great, you first have to understand the absolute mess that these old-school hubs used to make. And it all boils down to one big problem: collisions. And this brings us to a key idea: the collision domain. Just picture that crowded room again, right? What happens if two people try to shout at the exact same time? Well, their words just smash into each other and it all becomes nonsense. Nobody understands anything. That's exactly what a hub-based network is like. The entire network is one single giant room, one big collision domain. So if any two computers try to send data at the same time, bam! Their data packets collide, get corrupted, and the message is lost.
So you can see the problem with hubs, right? It's pretty obvious. First off, everybody has to share the exact same, very limited bandwidth. Not only that, they're forced to listen to every single conversation happening on the network, even if it has nothing to do with them. And here's the kicker. The more devices you add, the more shouting you get, which means way more collisions. The whole thing just slows down to a crawl, and pretty soon, the network becomes almost completely useless.
And this is where our hero comes in, the switch. A switch is just brilliant. It completely solves this problem by taking that one giant chaotic collision domain and shattering it into tiny little pieces. See, instead of one big room, it gives every single device plugged into it its own private dedicated line. It's like giving everyone their own personal phone booth. No more shouting, no more collisions, problem solved.
Okay, but wait a second. This brings up a really important question, right? If a switch is creating all these private connections, how in the world does it know where to send anything? I mean, you don't plug it in and configure it with a map of your network. The answer is actually so simple and so elegant. It literally teaches itself.
This whole process has a name. It's called backward learning, and it happens in 3 super simple steps. First, the switch just listens. It pays attention to the traffic coming in. Second, from that traffic, it learns where the device that sent the message is located. And finally, it makes a decision. It will either forward the message directly to its destination, if it knows where that is, or it'll flood it to everyone just to find it.
So check this out. The second you power on a brand new switch, its brain, which is called a MAC address table, is literally empty. It knows absolutely nothing. It has no idea which computers are plugged into which ports. It's just a totally blank slate, sitting there waiting to learn.
Okay, so let's watch this happen in real time. Imagine a computer, let's call it Station A, is plugged into port E0, and it wants to send a message to Station C. The very instant that message hits the switch, the learning process kicks off.
And this is the learn step. It's so cool. Before it even thinks about where the message is going, the switch looks at where it came from. It sees a packet arrived on port E0, and it immediately jots down that device's unique identifier, its MAC address, in its table. And just like that, boom, it now knows exactly where Station A lives on the network.
But there's still one problem. It knows where Station A is, but it has no clue where the recipient, Station C, is. So what's it going to do? Well, for this one time, and only this one time, it kind of acts like a dumb hub again. It shouts, or as we call it, it floods the message out to every single port, except for the one it came in on. It's basically yelling, "Hey, is Station C out there?"
And of course, when Station C eventually replies back to Station A, the switch is listening. It'll see that reply, learn its location, and add that to the table too. You can see what happens, right? As more and more devices talk to each other, the switch just passively and automatically builds a complete map of the entire network. And pretty soon there's no more flooding at all. It's all just quiet, super efficient, point-to-point delivery.
All right, so switches are amazing. We've established that. They're fast, they're smart, they're efficient. So naturally, the next thing you want is for your network to be reliable, right? So you think, hey, I'll add some backup links between my switches, just in case one cable gets cut. A fantastic idea for redundancy, but whoops, you've just accidentally created a brand new and frankly terrifying problem. The dreaded loop.
And this problem has a very appropriate name, a broadcast storm. Here's what happens. You know those messages that are meant for everyone on the network? Well, if one of those gets into a physical loop between two switches, it gets trapped. It just gets forwarded back and forth and back and forth endlessly. It creates copies of itself, multiplying like crazy until it eats up every last scrap of available bandwidth, and the entire network just grinds to a halt.
Let's walk through just how catastrophic this is. So, a broadcast packet arrives at switch A. It's doing its job, so it forwards that packet out of all its ports, and that includes the port that's connected directly to switch B.
Now, switch B gets that broadcast. And what does it do? Its job. It forwards the packet out of its ports, including the one that leads right back to switch A. And now you see the problem. Switch A gets the packet again, sends it to B again, who sends it back to A again, forever. This cycle just repeats, faster and faster, in an infinite loop that can literally crash your network in seconds. So this is the big takeaway. Redundancy is great, we need it. But active loops, they are an absolute network killer.
So, how do we solve this? How do we get the safety of having those backup links without creating these insane network-destroying loops? Well, it turns out there's yet another piece of network magic, a protocol that basically acts like an invisible traffic cop, keeping everything safe. And it's called the Spanning Tree Protocol, or STP for short. Its entire job, its only reason for existing, is to look at the physical map of your network, find any potential loops, and then it just intelligently blocks one of the links. It disables just enough connections to prevent a storm from ever happening while keeping that blocked link ready to go as a backup.
So how does it actually do this? It's pretty cool. All the switches on the network hold an election to pick one switch to be the root bridge. Think of it like the king of the network. Once the king is chosen, every other switch figures out its single best, fastest, most direct path to get to that king. Any other paths, the redundant ones that could cause a loop, are put into a blocking state. They're just sitting there on standby, ready to spring into action in a split second if the main path ever goes down. Okay, so let's recap. Our network is now fast because of switching. It's resilient because of spanning tree. But we can add one last really powerful layer of organization. And this is all about security and management, right on top of the same physical gear.
And we do this using something called VLANs, which stands for Virtual LANs. A VLAN is amazing. It lets you take one single physical switch and basically chop it up, logically, into multiple totally separate virtual switches. So you could create a VLAN for the sales team, another one for engineering, and a third one for HR, all on the same box. It's exactly like putting up virtual soundproof walls between those departments. Their traffic is completely isolated from each other. Great for security, great for performance.
And this gives you a really powerful security boost. See, because VLANs operate at what we call Layer 2, the data link layer. Traffic just can't cross from one VLAN to another on its own. It's just not possible. If you want the sales VLAN to be able to talk to the engineering VLAN, you have to intentionally add a Layer 3 device, like a router, to act as a bridge and specifically allow that traffic to pass between them.
So when you step back and look at it, we went from these dumb, chaotic hubs that just shout at everyone to these incredibly smart switches that literally learn the map of the network on their own. Then they get protected from self-destruction by this invisible traffic cop called Spanning Tree. And finally, we can slice them up into secure, virtual zones with VLANs.
It really makes you wonder, doesn't it? From this silent learning to these invisible cops, what other hidden, brilliant protocols are working tirelessly right now just to keep our entire digital world from falling apart?